morning, everyone. This is going to be a fairly short webinar on off-grid system design. It's a pretty big subject, so really this is just going to be more of an overview than something that's in-depth. Off-grid systems in general are a lot more complex than grid-tied systems are. So there's a lot of details in designing a system, but I'm going to go through the basic details of the information you need to gather for the site and details on sizing the PV arrays and batteries and inverters and all that kind of stuff. So let's just jump in and get started right here. First, what is an off-grid system? It's basically any system that doesn't have access to the electrical grid. And in these systems, batteries are generally used to provide for loads when it's dark or cloudy, when there's no sun or other production sources. And these are often referred to as battery-based systems. In these systems, modules, racking, a lot of the other components are often the same as what's used in grid-tied systems, but lots of other components are very specialized. So there are several different kinds of off-grid systems. There's PV or wind direct systems. These are where loads are run directly from the renewable energy source, don't have any storage, no batteries, for instance. And these are typically used for loads such as pumps and fans and running motors, which can run directly off from an energy source and often at variable speed because the production source is going to be variable. Some systems are DC only, that only have DC from a battery. Battery is charged by other sources like PV or wind or hydroelectric or generators. Other systems are AC only, where all the DC is converted to AC through an inverter or an AC generator. And this is really the most common type of off-grid system used for homes. Back in the old days, homes were dual wired in AC and DC because many DC appliances, in particular lighting, was more efficient. But these days, AC lighting is much more efficient. Plus, inverters have gotten so much more reliable that there's no reason really to have DC in the system at all. So, sometimes you might want a DC light in the battery or equipment room just in case there's a problem with the AC system. But generally, all loads are AC. Some loads have both, like I said, really fairly common for things like RVs and boats still. And then there's what we call hybrid systems, which are systems that derive energy from more than one source. So it might be PV in a wind turbine or PV in a hydroelectric turbine, or it could be PV in the electric grid where the electric grid is just a backup, or more commonly PV in a generator. So when designing these systems, there's a lot of difference between designing an off-grid system and a standard grid tie or net metered system on the grid. Many of you may be more familiar with grid tie than off-grid, so this is kind of a slide that just shows some of the differences here. In grid tie, the energy production that we're aiming for in the design is based on the yearly consumption. So in a grid tie system, you might make a lot of energy in the summer and be able to use the credits for that energy in the winter time. So if we look at yearly production to try to minimize or zero out a utility bill. In an off-grid system, the energy production is based on a daily or weekly consumption. We can't produce energy in the summer and store it long enough to use in the winter in most cases. So we have to look at more pinpoint kind of production, and that affects our system design and sizing. In a grid tie system, some of the energy is used directly as it's produced, because in general it's done at AC through a grid tie inverter. And some of the energy is sent to the grid and is stored as credit in a net metered system. In an off-grid system, energy can be used directly during the day, or energy is stored in batteries or other storage devices. Grid tie system, the PV array size is based on the yearly energy production. In an off-grid, the PV array size is based on energy production during the darkest time of the year. In North America, that's generally in winter, and of course in South America, that's going to be, in what we call the summer, but it's their winter months. But depending on where you are around the world, the darkest time of the year is not necessarily January or December. You might have, for instance, a monsoon season in June, and that might be your darkest month. And you do have to size it, based on the darkest month, since that's the time of least amount of energy production. In a grid-tied system, the inverter size matches the array size. So if you have a 5 kilowatt array, you generally have a 5 kilowatt inverter. You might have a 6 kilowatt array with a 5 kilowatt inverter, but those two sizes are pretty well matched. In an off-grid system, the inverter, it really has very little to do with the PV array size. The inverter is sized based on the peak AC load, not the array size. The array size is based on producing enough energy for the day or the week, but the inverter is used to run loads directly and is not really part of that energy production cycle. And I'll explain that a little more later. Grid-tied systems are generally very simple, very few components. It's generally just PV and racking and a grid-tied inverter, some switch gear, that's basically it. Off-grid systems are a lot more complex. It's charge controllers and monitoring devices and other things that you need to operate. Plus, as soon as you add batteries to a system, the complexity goes way higher. In a grid-tied system, if the system fails or is not designed properly or something like that, the lights still stay on. It's just an energy production source to offset a utility usage bill. But an off-grid system, if the system fails, the lights go out. So be aware of that with your customer, because when you install an off-grid system for a person, you essentially become their utility company. If they have a problem, and that problem, in my experience, always happens either on a Friday night or a Sunday morning or on Christmas Eve, you're the one that's going to get the call. So make sure that you do your design properly and make the system robust enough that your customers are happy and you're not having to go out there real often to tweak things and make adjustments. So here's a basic diagram of an off-grid system design. I have a PV array in the upper left corner. Generally, in most of these systems, there are strings of 3 modules in series. So in most systems, you have multiple parallel strings. So they use a combiner box to combine those parallel strings into a single output, which then goes to a charge controller, as you can see here, and through a set of DC breakers on each side of the charge controller. And then that energy goes really directly to the battery. We're showing a DC bus here in the power center, and that's basically an extended battery terminals, really. So it's PV through a charge controller to the battery, and that is your charging system. You might have other energy sources, such as a wind turbine or hydroelectric. And then the inverter can draw energy off that battery bus and power loads. And you might also have a generator that produces AC that can go through the inverter, and the inverter can charge the batteries and the generator can run loads at the same time too. You also need, in an off-grid system, need a battery monitor. It's not completely essential for running the system. It's kind of, but without one, it's like driving a car without a gas gauge. You just don't really know what's going on. You're kind of flying blind. So really, every off-grid system should have a battery monitoring system of some sort. Many of the inverter manufacturers have their own systems, and there are also third-party systems that can be used. So when considering off-grid system sizing, we have to remember that the purpose of the system is to power loads, not just to produce energy, as a grid-tied system would be, but we're actually running specific loads. So we need to know what those loads are, and we need to know how often they're used, how much power they draw, and we need to size our system based on that load analysis. So here's some of the information that you need to collect from your customer in order to properly design a system. And the first thing we need to look at is what the daily consumption is, or at least an average daily consumption. And this is, how much energy will the application consume each day? And is that seasonal? I mean, if you have, for instance, heavy air conditioning loads, that's going to be a heavy summer use. If you have a lot of lighting loads or other things in the wintertime, it might be a heavier wintertime use. So for each load, we need to multiply the power draw by the hours it's used per day to figure out what the kilowatt hour consumption is. Now for appliances, really the best way to estimate the energy consumption of appliances is to use the Energy Star ratings. This is particularly true of refrigerators and freezers. Excuse me. Hard to keep talking. So generally the yellow tag on refrigerators will tell you what a yearly energy consumption in kilowatt hours are. If you don't have the yellow tag, you can usually look it up on the Energy Star website. There's a link shown here, and look by model and brand, and it'll tell you. You'll get a copy of the yellow tag that you see in the stores, and that tells you what the kilowatt hour consumption is for the year. And if you divide that by 365, you get a daily consumption. We need to know what the peak load is and the characteristics. Now, peak load is how many of these appliances or loads are being run at the same time. So we need to add up our loads, and they run simultaneously. There are some loads that won't. For instance, you might have a heater, although that's a pretty big load for off-grid, and you might have an air conditioner. Well, you're not likely to be running both of those at the same time. But we do need to look at things like you might have a washing machine running and you might have a well pump. Well, those two might run at the same time. And refrigerator could go on while all that's happening. So we do need to pay attention to what loads are going to run at the same time and make sure that our inverter is large enough to carry those loads. There may be separate AC and DC loads, although, like I said, DC loads are pretty rare in household systems. And of course, we need to know what the voltage and frequency of the loads require. Of course, here in the U.S., most houses are 240 volt AC, single phase. But if it's overseas, it might be 50 hertz at 230 volts, or there's a variety of voltages around the world. So we need to know that. Then we need to estimate the days of autonomy. And this is how many days in a row will the load needs to run with little or no sun. If you're in an area that has, very dark winters or lots of snow cover, that kind of thing, we're going to need a battery storage to carry through those periods of low sun. And then we need to find out what the sun hours per day are in the darkest month of operation at that location. That's the available solar resource that we have to work with. And generally with off-grid systems, we use winter solstice time frame rather than the annual average, at least if the loads are run during the winter. If it's, say, a summer vacation cabin, we don't necessarily have to do that, but a year-round home certainly does. So developing a load analysis is really the first place to start. We do have a worksheet in our catalog. Actually, it says 2016 catalog here, but we're on 2017, going to 2018 shortly. But we have a form in there that gives you an idea. It's kind of a template to use to calculate what the loads are. We also have this in Excel spreadsheet form that we can send you, which is fairly easy to work with. And one thing to also not forget is what we call phantom loads. Many loads, many appliances, when they're plugged in, even when they're turned off, will actually have some draw. And it's generally not much, but it can add up pretty fast. So if you see this list, which was developed jointly by the California Energy Commission and the U.S. Department of Energy, these are fairly common loads to have in a modern house. Computer and speakers and routers and cell phones and satellite cable box, maybe plasma television. You can have a microwave oven. Anything that has a digital display that's on is going to draw energy. And these things add up. And like you can see from this list, it's about 123 watts. Well, running 24 hours a day, that's almost 3 kilowatt hours of energy in a day. So we need to be aware of these phantom loads and don't forget to use them. I do recommend putting as many of these loads on switchable outlets or plug strips to turn them off in times of low sun to reduce consumption. So here's an example of our Excel spreadsheet form doing a load analysis, and I just kind of filled in a bunch of things here. For instance, a furnace blower of 250 watts, and it's run 5 days a week. So it's consuming 1,250 watt hours a week. We use a weekly basis and then divide by 7, and that gives us an hour, an average daily consumption, because we just go in a day. For instance, you may not run a washing machine every day, but you're going to do it a certain number of times a week, maybe. So it's best to kind of average it out of a week's worth of data. This is a basic list here, and it's showing, at the bottom here, peak watts is just roughly 5 kilowatts of load. That's with everything running at the same time. And again, not everything may run at the same time, but robust system design, you really want to account for that. and we're showing about 7.5 kilowatt hours of consumption. But we have to adjust that for inverter efficiency, since inverters are not 100% efficient. So really, we're looking at about 8.5 kilowatt hours a day consumption at the bottom here. This is just an example. So then we need to do a site analysis. So what's the solar potential of the site? What's the peak sun hours? What are the seasonal effects? How much shade is the PV site going to get? Are there orientation issues? Is it, a lot of trees or cover, that kind of thing? Might be mountains or other buildings that might shade a PV array space. We need to be aware of that. We need to find out how much space, of course, to mount a PV array. And PV arrays for off-grid systems are, again, based on the peak sun hours during the darkest month, not the yearly average. And one thing when siting an array is to make sure that you have as much wintertime sun as you can get at the site. There may be other possible energy sources other than PV. So is there wind potential at the site or micro hydroelectric potential? Hydroelectric is a wonderful way to produce energy in mountainous areas. You have to put water in a pipe and run it down a hill to get pressure, and then you can use that flow and that pressure to develop energy. And a site that has that potential should definitely be looked at to be developed, because it could be an excellent alternative or addition to a PV system. And obviously wind and hydro turbines can produce power when sunlight's not available. So anytime you can produce some energy when sunlight's not available, you're making your PV system all that much more robust. Then we need to kind of base a design on how many cloudy days in a row we're going on. Obviously, the weather is unpredictable, but we can get a basic idea of weather patterns in an area. And, certainly if you're doing these kind of installations in an area where you live, you should be fairly familiar with the weather patterns there. And out of that, it's very hard to do a year-round off-grid system in most places of the country without having a backup generator. It's almost impossible in most places. Sunny deserts might be an exception, but in most places around the country, you're really going to have a backup generator. But how much the generator runs is really the question we're going to look at here. Obviously, you want to have your generator runtime as minimized as possible. Generators are very expensive, fuel's expensive, they're noisy, they're dirty, all those kind of things. So anything that we can do to reduce that generator runtime is going to help have a better system and a happier customer. But you generally are going to have a backup generator of some sort to be able to carry over for long periods of cloudy weather. So we get into PV array sizing, and obviously we have to find out what the peak sun hours. There's a number of sources for that. National Renewable Energy Lab has their Red Book, which has excellent data collected over 30 years for every month at multiple locations around the country. So that's a great source to do it. We do have maps in the back of our catalog. These maps cover the world. They're kind of rough. I mean, obviously, a world map is not going to have details of microclimates of specific areas, but you can still get an idea of what the sunlight potential is in all these different areas. Now, these maps are for the darkest month of the year around the world. These are not the yearly average on these maps. So don't use these maps for grid-tie systems. That's not going to work for you. But these are excellent as a quick reference for off-grid systems. Another source, there are lots of online sizing programs or programs that you can purchase. PV Watts is an excellent source to do. You can enter in data for an area. This particular shot here is Knoxville, Tennessee. And as we can see here, even though in July, they have about 5.5 peak sun hours or 5.5 kilowatt hours per meter squared of sunlight, in the wintertime, it's much less than that. So the lowest here is December, the 12th month at 3.22, although January is not much different at 3.23. But those are the numbers that we really need to design a system for, not the yearly average of 4.66, which is what you would use for a grid tie system. Just using our example from that load analysis, our loads and our inverter are consuming about 8,533 watt hours a day. We multiply that by a factor of either 1.2 or 1.25. I like using the 1.25. It gives a little bit more leeway in there. And this is the energy used that the PV array actually has to produce each day, because the 1.25 factor accounts for battery charge discharge efficiency losses over the life of the battery. New lead acid batteries are roughly 90 to 92% efficient in their conversion, but as they age, the efficiency goes down. So we need to size the system based on the lifespan of the battery. That's why we kind of do that heavy 1.25 factor. So in this particular system, we need to produce about 10.5 kilowatts of energy each day. And as we saw from the location, we had 3.22 peak sun hours. So that, do the math there, that means we need a minimum PV array of about 3,313 watts. And again, this is a minimum. These sizings are giving us a minimum here. Certainly oversizing the system is going to, make it more robust, carry it through more inclement weather, and just be a better system here. But we need to see what our floor is as we're doing a system design, and make sure that we're at least accomplishing the bare minimum here. So at 3,313 watts, and if we use, say, a 280 watt module, that's about 11.83 modules. Well, obviously round up to 12 modules there. But again, that's a minimum. So going to 15 modules or more is going to make the system more reliable, but we need at least 12 modules of a 280 watt rating for this particular system. And this is, of course, assuming a full sun site with no shading issues. You have to take that into account on your array sizing. So when we go to battery banks, then we also use the load analysis, which is telling us about 8.5 kilowatt hours a day or 8,500 watt hours a day. And we need to convert those watt hours or kilowatt hours into amp hours, since batteries are rated in amp hour capacity in general. These days, we're seeing much more kilowatt hour ratings on batteries, particularly lithium ion batteries and batteries that are used for load shifting on the grid and that kind of thing. But really, most lead acid batteries are rated in amp hours, and it's a simple conversion. Essentially, you take the watt hours of consumption, you divide that by the battery voltage. In this example, it's 48 volts DC, and you come up with about 178 amp hours per day of consumption. And that's based on the C20 rate, or the capacity of the battery divided by 20 rated battery, to get that number. One thing about batteries, the more quickly you draw energy out of them, the less apparent storage they have. The more slowly you draw energy out of them, the more apparent storage they have. And the general point where most batteries are rated is at a 20-hour rate, or the capacity divided by 20. So this would be 178 amp hours at the C20 rate. Now, if you're in a sunny winter area, you should have at least 2 days of energy storage. Obviously, not every day is sunny. You're going to have to, go over a few cloudy days. Even on a cloudy day, you often get some energy production, but it's not going to be very much. So we have to have storage for that. We generally size lead acid batteries for a 50% depth of discharge. You can go down to 80%, but for maximum battery life, you don't want to go down below 50 very often. So we size for 2 days of storage to a 50% depth of discharge. So really what you do is you multiply the daily amp hour consumption by 4 for that 50%, because 2 days would be 50%. And we end up with a rating of approximately 712 amp hours for the battery bank. Now, if you're in a dark winter area, you should have more energy storage. So we go to 3 days of storage to a 50%. And so we would multiply the daily amp hours by 6 in that case, and end up with a 1,068 amp hour battery bank. And again, these are somewhat minimums. We really want to have this kind of minimum setup. There's no reason not to have, 4 or even 5 days of energy storage if you have a lot of extended storms. Batteries are expensive, however, so it might be more cost effective to just run the generator more for those extended times than it is to try to store the energy in the battery. And as I said at the bottom here, the battery size can even be reduced more than this if it's acceptable to have the generator run times be longer, to run it more often or for longer periods of time. But if we're trying to reduce the generator run times, we're going to want to increase the size of the battery. So one thing to also be aware of is battery charge rates. Most lead-acid batteries should not be charged at a rate greater than approximately C/5. Capacity in amp hours divided by 5. So, for example, a 100 amp hour battery should be charged at rates of 20 amps or less. You really shouldn't charge it harder than that. Some manufacturers allow harder charging. Certainly other battery technologies might allow for harder charging. But at this point, lead-acid batteries are still pretty much the standard in these kind of systems. I think we're going to see more advanced battery designs in the next few years that may be highly competitive. Right now, they're a lot more expensive. They're not well integrated into the off-grid equipment yet. So we're still pretty much standardized on lead-acid batteries at this point. So kind of going through some sizing results here, the load analysis told us that the inverter needed to be rated for about 5,000 watts. You could probably use a 4,000 watt inverter if your customers are aware that they can't just turn on every appliance in the house at the same time. So a lot of this may depend on your customer. If they don't even want to think about their energy production, they want it just like downtown, you're going to really want to make sure that you have an inverter that can cover every load that's running. If they're much more energy conscious and willing to adjust their energy usage based on their system, you may be able to use a smaller inverter. But this really does call for a 5,000 watt inverter here. The load out analysis also told us that the loads, including the inverter losses, consumed about 8,533 watt hours a day. The site analysis told us that we had to size the array for 3.22 peak sun hours. The load and site analysis results times 1.25 told us the minimum PV array of 3,313 watts, which is 12 280 watt modules approximately. Daily consumption was 178 amp hours, which, as we had in the previous slide, worked out to at somewhere between a 700 and an 1100 amp hour battery, depending on the amount of autonomy that we're designing for to carry over for windy weather. So all this information is coming out of doing a load analysis, doing a site analysis, and doing an analysis of what your customer needs to run those things. You have to adjust these things seasonally, adjust them for local weather conditions, those kind of things. But that's essentially how we come up with a system design. So then after, once we know our numbers, then we have to make choices as to what we're going to use. So which type of battery, flooded battery, sealed AGM or gels, or advanced technology, might be lithium batteries. It looks like Aqueon saltwater batteries might be back on the market shortly, so that might be another choice. And lots of things to consider here. What's the maintenance schedule? Flooded batteries, for instance, have been very popular for many years for off-grid systems, but they do require routine maintenance. And some customers are good at that and can get flooded batteries to last a long time. Other customers don't do that and will not do that, and flooded batteries will fail rather quickly if they're not maintained properly. So for those systems, you really want to use a sealed design, such as an AGM or a gel, or some sort of advanced technology. You also have to consider shipping, handling, storage, costs. There's a lot to go through with batteries to make sure you get the right battery for your customer. One thing I did run into when I was doing lots of off-grid installs for people is in those years it was mostly flooded batteries. I did find that most people that were new to living off-grid tended to ruin their first set of batteries just because it's kind of a learning process to learn how to operate your system. So I tended not to put in the highest grade, most expensive batteries to start with, kind of do a starting set, and then if they can get a good lifespan out of that, they can move into a more expensive industrial grade battery or something like that. We need to choose what our battery voltage is. Now, 48 volt is going to be the most cost effective for most household systems. For any systems really over about 2 kilowatts of inverter size, you really want to go to 48 volts. But 12 and 24 volts are certainly usable for small systems, standalone systems, vacation cabins, marine and RV, data collection, those kind of things, weather stations. A lot of those are still at 12 or 24 volts. So that can happen. So we need to know what the voltage is. We do need to choose our charge controller type. Most systems these days use MPPT controllers because most systems have 60 cell modules in them. 60 cell modules are not a direct voltage match to battery voltages, so they do have to go through conversion through MPPT. But smaller systems can still use pulse width modulated controllers. With pulse width modulated, essentially the PV array voltage has to match very closely what the battery voltage is. So we use either 12 or 24 volt nominal modules. A 12 volt module is 36 cell and a 24 volt is 72 cell. Again, a 60 cell module doesn't really fit in there. It's not quite enough voltage to charge a 24 volt battery. It's too much voltage to charge a 12 volt battery directly, although it can be done. You just get much less power out of the module. So really, pulse width modulated controllers are used for smaller systems, and most systems these days are going to use MPPT or maximum power point tracking controllers. They actually do extract more energy from a PV array or are available in a lot of array voltages up to 600 volts DC. If you have to run wire a long way, you might have, for instance, a house in a shaded location, and you might have an open field, 300 feet away. It's a big wire run. You're going to need a higher voltage charge controller to get that energy to the battery system. One option might be there is to put the battery system and the inverter system in a small building out where the array is, and then run AC to the house. That's another option. But more generally, the batteries and the inverters and whatnot are located at the house location, and the PV array is just done at a higher voltage to cover that distance. Then we need to choose our module type. Is it going to be 36 cell modules, 60 cell, or 72? 60 and 72 cell modules are much less expensive per watt, so really those are the ones that are generally used for most systems except for very small systems. And we need to consider transportation and mounting limitations as well as module cost per watt. Larger modules are more expensive to ship, harder to carry if you have to carry them long distance, that kind of thing. But they are cheaper per watt. So hopefully that was a covered an overview, and I'd be glad to answer any specific questions.
All right, thanks, Brian. We'll go ahead and dive into some questions here. I've seen a lot of good ones.